Good day, everybody. Today we're going to look at finding the average value a planet is to the sun. And we're going to use Kepler's laws. So each orbit of a planet will be in an ellipse with the sun at a focus. Here we're looking at different eccentricities. And well, there's going to be different averages. There's going to be one, say, with respect to time. Right? So if you took, say, how far away a planet is once an hour and then average over the course of a year, and that would be one way of averaging with respect to time. But there's also with respect to arc length or angles or projection onto the major axis. So we're going to quickly look at all of that. So here's again 4 eccentricities. This represents the eccentricity of Earth's orbit. This represents the eccentricity of Pluto. This represents the eccentricity of Eris, dwarf planet, and here's the eccentricity of Halley's Comet. Here I've drawn them all, so they all have major axis of 2. We're kind of normalize. So they all have major axis 2 or semi-major axis 1. And I'm going to piggyback off the results from a couple of articles here. One, just average distance of the Earth from the sun. This one I need to do a correction on. So they found the average value with respect to the projection incorrectly. So I will show that correction. Another one, so mean distance in Kepler's third law. So let's begin. So first we're going to look at average value with respect to angle. So here's Earth. It's nearly circular, so we can't see too much distinction between the difference between an ellipse and a circle yet. But there's known formula for plotting an ellipse with a focus at the origin. This is it. And so we'll just put in our different eccentricities and one for A. So there's the plot, and we can get the different R's. Here it is with Pluto. Start to see a little more difference. Make it more extreme. Here's Eris. And again, we can kind of see that for half the angle range, we're going to go from 0 to pi, say for the upper half ellipse, and then there's symmetry. For 0 to pi, if I look at first 0 to pi over 2, we're really close. And then we only reach, say, r equals 1 with this angle 2 pi over 3. So there's only 60 degrees left to be bigger than 1. And on the most extreme case, 0 to pi, we're really small. And even at 11/12 pi, we're still less than 1. So it's kind of obvious we're going to be smaller than 1 for our average value with respect to angle. Let's look at some of the math. So here's the math for the finding the average value with respect to angle. First, a few general ellipse facts. Again, we're going to use A for the major axis, B for the minor axis, C will be the distance the focus is from the center. And you've got this equation, the major axis squared is b squared plus c squared. So b is going to be a times the square root of 1 minus e squared, because the eccentricity is defined as c over a. So if you put that in, that's what you would have, right? So c is equal to ea. Should have put that. So C equals EA. If you put that in there, then you can solve for B in terms of A, and we get this. Anyway, so if we look at different angles, find the R, the definition of average value, you want to integrate R with respect to theta divided by the total change in theta. So that would be 1 over 2 pi. So if I put in the rule for R, this is a doable integral. it's a tough antiderivative, and then you have to kind of piece it together to go from 0 to 2 pi, or use complex analysis to get it. But regardless, this will be the result. So it ends up being B, the minor axis. And of course, B gets closer to A the more it's circular, but as the eccentricity increases, B, like Halley's Comet, decreases. So the average value can get quite small. If I verify it numerically, so I put in the eccentricities of those 4 orbiting objects and found the R for each one of them. Then first I'll have the software Maple do my general antiderivative. So there it is. So it can do that antiderivative, or more specifically for the one I want A over 2 pi times that. And so it comes out to be that, which is B. But if I ignore that and just do the integral, so if I integrate the R formula for the Earth divided by integral 1 to 2 pi, then I get that value, so almost 1, which is what B is. So this will be B. If A is 1, B will just be the square root of 1 minus the eccentricity squared. For Pluto, start to see a little bit of a difference. So this will be the integral, and comparing it to B, same thing, a little bit of rounding error, ignore that. There's a plot of R, and then the average value is just below 1. It's kind of hard to distinguish there. Here it is for Eris. Do the integral, compare it to B, identical, pretty much, a little rounding error. And then the plot. So here's a plot of what the average value would be. And lastly, Halley's Comet. So there we go. So the most extreme, the average value is really low. Next, we're going to look at average value with respect to arc length. So if I look at how far I've traveled around the ellipse, again, this one's nearly circular, so it's almost like, since A is 1, it's almost like a unit circle, but it's a little bit off. But there's the distance we've traveled. We're going to use this formula for how far we've traveled to get our average value. But there it is for Earth's orbit. For Pluto's orbit, the S, I already did the top half. By symmetry, the bottom half would be similar. So we can find our position. It is for Eris's orbit. And now things balance a little bit more, because by the time we reach 1, have we gone roughly half the arc length? Yes. And similarly for Halley's Comet. So before 0 to pi over 2, half the total angle, we were really small. But if I look at where half the total arc length is going to be, it's right about where R is 1. So there's a lot more balance there. In fact, here's what this crazy curve looks like. This is going to be the work for finding the average value. Again, here's a general formula for ellipse with a focus at the origin. Here's a formula for the arc length of a polar curve. So my infinitesimal amount of arc length will then just be this. And I went ahead and found dr d theta. All right, just think of this to the -1 power, so multiply down by -1 times that. This whole thing to the -2 power. Derivative of what's inside simplifies to that. So that's dr d theta. So ds is going to be the square root of r squared plus dr d theta squared. And you've got a lot of things in common, and they're all squared, so you can pull it outside the root these will all be positive, so I don't have to worry about absolute values. So if I factor all that out, the square out, comes out this way. I have 1 plus this squared. If I get a common denominator, then I can pull out another square. So I multiply this one by one more. So now this is squared, and then this square root. Right? And if I square this, I'll get 1 plus 2e cosine theta plus e squared cosine squared. But e squared cosine squared plus e squared sine squared will just be the e squared. So this is the ds. So for the average value, I want to integrate over the full length of the ellipse, r ds over integrate ds. And so I plug in for r and ds. It's now in terms of theta. Theta will go 0 to 2 pi. There's ds again. There's similar integrals. I've got an a times 1 minus e squared, well, twice, because here I have an r and then this with a square. So if I factored that out, a squared 1 minus e squared would pull out of the top integral, but a times 1 minus e squared pulls out of the bottom integral, so you can cancel. So I'm still left with 1 though. And then in the denominator here, I have 1 plus e cosine theta cubed, the square root on the top. In this bottom integral, I just have the square root and 1 plus e cosine theta squared. Right, so it's a similar integral. This one I'm not sure if it's doable, but the answer is A, so the semi-major axis. So average with respect to arc length is going to be the semi-major axis, A. And that we can actually show even if we can't get the antiderivatives, the integral. And I'll do it numerically, but before I do, let's look at it just with this argument. So we've got this ellipse, and it doesn't matter where I put the x and y. That's not going to matter. But we're going to integrate ds. And if I integrate from 0 to all the way around, so 0 to L of r ds, that would be the same as integrating 0 to L of this distance, where the other focus is. Right? So I mean, you can just put that imaginary point there. So where that focus is, I find that distance. I mean, if you think about it, the top half, here I've got the origin here, but if you find the integral of the top half for this r, that's going to be the same as the integral of the bottom half for this r star. And conversely, if the integral of the bottom half for r is like the integral of the top half for r star. Anyway, so if I integrate 0 to L of r ds, that's going to be the same as r star, where r star is the distance to the other focus. So if you go all the way around. But if I integrate their sum by the property of ellipses, at every point on the ellipse, the distance you are from both foci is going to be 2a. So the sum of the two distances there is always 2a at every point on the ellipse. So this integral will be 2al. So if I just integrate r, since these are equal and their sum gives you 2al, each one was a times l. And then so for the average value, I want this, but now I know this numerator is a times l, and the bottom is just going to give me l. So we can actually get the value that way. And we're going to do that a couple more times. If I check numerically what I just did, so there's the total arc length. This one's for Earth, the arc length of the ellipse for Earth. It's a little under 2 pi. Here's the arc length function So I did this two different ways. I did it with the ds, so I can integrate r ds and divide by ds. So I define ds and then integrate r ds, divide by the integral of ds, and of course its value is 1 because I made the major axis 1. In general it'll be a. Or using my simplified formula, where I had the 1 minus e squared, this square root divided by cubed, and square root divided by squared. It'd be the same thing, 1. And for the other planets, similar. So here's the total arc length for the ellipse with Pluto's orbit, semi-major axis 1. Here's the arc length as a function of theta. So I can find ds in terms of d theta and integrate r ds and also integrate ds. And of course it's 1, or using my simplified formula, it's again 1. And if I plot r with respect to s, the average value will be 1. Again, there's the formula for the total arc length. We're dropping below 2 pi significantly now. Here's ds in terms of d theta, integral of r ds divided by integral of ds, or equivalently the simplified formula. And a plot of r with respect to s, and its average value will be 1. And lastly, with respect to Halley's Comet eccentricity, so there's the arc length, about 4.3. So again, we're dropping pretty significantly from 2 pi. Notice kind of 4 is the minimum. I mean, if the major axis is 2, you have to go 2 across, back and forth. So we're near the minimum, somewhat near. Anyway, so there's the arc length as a function of theta. So I can integrate, well, I can find ds in terms of d theta, essentially. And then there's r ds divided by integral of ds is 1. Or using the simplified formula I had, 1. And the plot of r with as a function of s. Next, we're going to look at the average with respect to time. That might seem reasonable, right? So how far away are we from the sun with respect to time? So here we'll have to use the fact that the planets will sweep out equal areas in equal amounts of time. So, and then we know the formula for the area in terms of theta, 1/2 r squared d alpha, if I want my upper limit to be theta. So I can get the time in terms of theta. So let's just look at the times for different planets. So there's Earth. I normalized it, so the total area of an ellipse is pi AB. So if I divide by pi AB, then I'll go once around at time t equals 1. So then these t's are the fraction of the year being the period to go once around. Of course, it takes 0.5 of a year to go half. Here we are for Pluto. Here's the times, a little bit eccentric. Here we are for Eris, the times. You can kind of tell, so by Kepler's law, equal areas, you're going to go faster the closer you are to the sun. So here's the math we will need. Okay, so there's our r. For area, it's 1/2 r squared d theta. This is the polar form for the ellipse as before. This time I did a little bit extra. I found a of theta and did a dummy variable, and then t for any theta, as I did on that picture, just changed it to alpha. So then I can plug in so I can use theta as the upper limit. So I use a different angle name here, namely alpha. I divided by the full area of the ellipse. I didn't have to, but then that'll mean that the time to go once around is 1. I can pick it so that will happen. So that's what I did. So if I divide by pi AB, the area of the full ellipse, then the time to go once around will be 1. Anyways, so we can find dt, d theta, and it'll be this. So essentially 1/2 r squared d theta. It's proportional to, and then depending on what you want to do, I put in a pi AB, 1 over pi AB. So the average value is you want to integrate from 0 to the period to go once around the orbit of r dt divided by 1 dt, and that's just going to be 1 over pi AB integral 0 to pi 1/2. So dt is r squared, so r dt will be a r cubed. And then we've normalized this, so this is going to be 1. But even if we didn't normalize it, so if I left that pi AB out, then I wouldn't have it here, but then this would give me pi AB. Right? So, I mean, either way, you're always going to get the same result, this. And this integral is doable. Yeah, not easy, so I'm not going to, well, maybe I have Maple do it for me. But it's going to end up being this. Another way, if you don't want to use the pi AB, again, if you know that time to go from one place to another is proportional to the area, then that means there's some constant. So dt is going to equal some constant dA. Again, I used 1 over pi AB. But regardless, if I want to find the average value, I want to integrate from 0 to the period of r dt, integral 1 dt. So I want to integrate over the full area of the ellipse, which even if you didn't know what it was, it didn't matter because we're going to change anyway. But it'll be r, and then dt is c dA. So if I put that in, then the c's factor out and of course cancel. And then dA, the important thing is that I know it's 1/2 r squared d theta. And then, I canceled the 1/2s as well. So it's also going to be this integral. So I could just do this integral, and again, it'll always be a times 1 plus e squared over 2. If I check this on my Maple software here, so first the full area, and compare it to pi AB. So pi A is 1, and then B is square root of 1 minus e squared. Of course, they're the same. With time to go around, this will be for half the orbit, 0.5. So again, I did it a couple ways. There's the dt, so I can integrate r dt divided by the integral of dt, and I get this value, which we'll see is 1 plus e squared over 2. If I integrate r cubed divided by the integral of r squared, this is cubed, but then I'm dividing by the square, so I went ahead and simplified that. But it'd be this cubed divided by that square, but anyway, simplifies to that. So again, I get the same result. Or so here's for the general result. So it's a little complicated, but if I integrate, this would just be the numerator for like the above, 1/2 r cubed. So it is doable. And if I divide by pi AB, but B is A times the square root of 1 minus e squared. then I get this. And if you distribute that 1/2, you get 1 plus e squared over 2 times a, as expected. Or, yeah, I think I essentially did the same work a second time here, but well, here's the r cubed divided by r squared. Again, I simplified this part. This would be cubed, but divided by the square, so it'll simplify to just that. But of course, we get the same thing. If you distribute that 1/2, it's 1 plus e squared over 2 times a. And if a is 1, it's 1 plus e squared over 2. So that's the same number I had here, 394450. For Pluto, then there's the area of the ellipse. It matches if I do the integral or pi ab, get the same result. If I measure time by normalizing, divide by the area, then there's the time to go halfway around it, and those different points I had on the picture. There's dt, integral of r dt divided by integral dt, or the integral of r cubed divided by integral of r squared. Same value, or 1 plus e squared over 2, simplest. So this average value is above 1. For Eris, I think we all trust the result at this point. So I just integrate r dt divided by integral of dt, or my integral of r cubed divided by integral of r squared, same value, or 1 plus e squared over 2. And lastly, Halley's Comet. Integral for different times, dt in terms of d theta. So there's the average value then for Halley's Comet. Or integral of r cubed divided by integral of r squared, same value, or 1 plus e squared over 2. Again, so if we look at Halley's Comet, we go much faster when we're closer, and then here when we're far away we go slower. So we'll spend half the year by symmetry this far away. So that's with respect to time. So here it is here. So with the 0.25, we're really far away, like at 1.5. So that's over half the year we're that far away. And then for the other half, looks like that. So now we'll look at projecting onto the x-axis. So I can find the x value and what's the r for each x value. So I've got it here with Earth. Here it is with Pluto. And well, you can see now that it's linear. Here it is for Eris's orbit. And here it is for Halley's Comet. Again, linear, so it's going to be easy to integrate. So again, we'll start with, we've got r in this form for polar. But this time I will, cross multiply. And, well, r cosine theta is conveniently x. So I can solve for what's r in terms of x. And now I just want to integrate over the range of x. Well, a is 1 for my problems. But regardless of what a is, right, if there's the center, the distance from the center to a focus is c, but c will be e times a. So this is a minus ea, and this is a plus ea in distance, but the x value will be the negative of that if I'm on a coordinate system. Anyway, so I want to do the integral. Of course, the denominator will be 2a, right? That's how far across you are. And then for the numerator, I want to integrate r in terms of x dx. So in a way, we're just doing the top half of the ellipse, although the bottom half would be the same. For each x, r, I drew it on the top, but r is the same on the bottom. The distance, the value. So regardless, but if I'm doing divide by 2a, we'll say it's the top half. Then by symmetry, it gives the correct average value. So it'd be this integral. This is a constant, so constant times the length of the interval would be times another 2a, so 2a times that. And then this, you get x squared over 2, and if you plug in the limits, it simplifies. I didn't show the work there, but to that. And so it becomes just a. So the average with respect to projection onto the major axis is a as well. And it's the same proof, just a different variable here. So again, if I integrate over the full range of x of r dx, I would get the same result if I integrated r star, where r star is the distance each point is to the other focus, right? Because by symmetry, however far away you are at one point, you'll be that far away from r star at another point. I guess the same y value, but on the other side. So this integral equals that integral. And again, the integral of the sum is like integrating 2a. So it's 2a times the length of the interval, which is 2a, so 4a squared. So if they're equal, and then their sum integrates to this, then each one contributed half, 2a squared. And so for the average value, it's 1 over the length of the interval, 2a, times that integral, and so it's a. So again, this is what was wrong in this article right here. So he tried to find it. So here's his work of doing some of the others, which were okay. Kind of used some of his notation. But onto the major axis. So his problem is he's got a square here, 1 minus e squared squared times 1 minus x squared. There should not be that square there. Go away. And so when he, and again here there should not be the square. So he's going to get the wrong values. He's got it with respect to projection under, because he multiplied by a number less than 1, but it should be 1, whatever the major axis is, and our major axis is 1. And again, looking at how he did it, so he changed it to, he centered this ellipse so that the center was at the origin. And then, so he had to integrate this, which I guess looked intimidating. But it's actually not bad. So I will do it. So again, we've got an ellipse. And there's our R. And so, but now my ellipse is centered at the origin. So I still labeled this as R, just to be consistent with the other examples I did. So how far away are we from this focus? Well, it's, the x distance squared. So how far away is any x value from this focus? It'll be x minus EA. C is equal to EA. And then plus y squared. Right, so that will give me, the square root of that will give me R for any point on the ellipse. And well, so what's y squared? Well, you can solve for y squared. It's 1 minus x squared over a squared, and then times b squared. You can factor out the a squared. C over a is e, so this will be 1 minus e squared. So that was the problem. It's 1 minus e squared, but not squared, times a squared minus x squared. Again, he used 1 for a, as I do as well, but I left it as a here. So that would be the difference. And so we want this will be our r, but it is linear. If I square it out, there's the first term squared. If I square this out, 1 times that gives me these two. Negative e squared times the other two give me those two. We've got some canceling. The x squareds cancel. Okay, cancel them. And then the e squared, a squareds cancel. So just to put it in the right form that I want it as a squared minus 2eax plus e squared x squared, which is a perfect square conveniently inside that radical. And I made sure so that when I pull it out, I won't need absolute values. This is always positive for the a's in question. If the ellipse is centered at the origin, the center's on the origin, then we're going to go negative a to a. So we'd have to integrate that from negative a to a. And so this square root we saw simplified to this. And again, we can see, so a times the length of the interval will be a times 2a, which will be 2a squared. The denominator is 2a. This part, I didn't bother with an antiderivative because it's an odd function with symmetric limits, so we know that part will be 0. Anyway, so we get a. So that's what he should have gotten. He should have gotten a. It's kind of interesting he didn't notice because the argument that he used for the ds, which I used, you can also use for the dx. I already did it for the dx. And it didn't matter where the origin was. Like here he does it for the ds with maybe the origin at a focus. But I'll just repeat the exact same argument, which again, it doesn't matter where the origin is. You can slide it over. This argument works regardless of where you want to put the y-axis. But so again, r star, dx. So it's the same argument, but now it's centered at the origin, so we'll integrate negative a to a, r. If you go all the way around, well, all the way around, if you go, let's just do the top half of the ellipse, integral of r will equal the integral of r star by the symmetry, and their sum is going to be 2a at every x. So it'll be 2a times the length of the interval, or 4a squared. So each one will be half of that amount, so 2a squared. So the average value is 1 over the length of the interval times that integral. So that argument worked here as well. In fact, the argument works. He didn't do this one. I did it with respect to the central angle. Right, so I kept it at the center and just found what about the angle with respect to the major axis, but with the center at the origin. So that angle. Right, so before we did it with respect to little r's angle. So if I do it with respect to that angle, well, I did the work to get it and do it numerically. So again, the equation of the ellipse, and then I want to put it in polar, and I wanted to keep little r being the distance to the focus, so I used big R for the polar. So x is r, big R cosine theta, y is big R sine theta. You can factor, solve for r, and take the square root, and then my little r is the square root of the same as before, right? X minus ea squared plus y squared. So that'll be r squared. R will be the square root of that. But x now, instead of what I had before, it'll just be big R, where big R is this, cosine theta. And y will be big R sine theta. So take square roots and you get your r. If you go all the way around d theta, of course you get 1 over 2 pi. So I just need to integrate r d theta, so it'll be that d theta. And we always get a. Again, by that same argument. if I integrate r of theta all the way around, it'll equal the integral of r star of theta all the way around 0 to 2 pi. Right? At each theta, r and r star are different. Their sum will give me 2a, but if you go all the way around, by the symmetry, you're going to get the same result. So again, if they're equal, their sum is 2a, so each one contributed half that, and so for the average value, it's that 2 pi a divided by 2 pi, so a. So I'll look at that numerically in a moment here. Before I do. So it seems like, wait, can I always use that argument? What about this, my first angle? So here it is. It would be true that the integral 0 to 2 pi of r of theta d theta equals the integral 0 to 2 pi of r star, but I had to change the angle, phi. Right, so whatever angle this makes, this is making a different angle. And we could actually kind of get this angle in terms of that angle, but it's not worth it. But they're at different angles. Now by symmetry, if I go all the way around 0 to 2 pi for theta, then integrating 0 to 2 pi of phi, those will be equal. But what I can't do this sum now, because I need to evaluate these at the same angle, theta. And so here's an example. If theta is pi over 4, r at pi over 4 is that. R star of pi over 4 would be that. So if the angle is pi over 4, there's r star and here's r. Right, so it's two different angles. So that's why that argument wouldn't work on this one. Or here it is at 90 degrees. Looks like that. And in fact, in general, r of theta is this. And r of phi, it's plus or minus for putting the focus. It depends on which focus you want at the origin. So it turns out r of phi would be this. And if I add them together, it's that. So anyway, it's not 2a in general, if you're evaluating at the same angle. Okay. So that argument doesn't work on this one. And again, just if we want to see verification, first with projection onto the x-axis. So there's that, and of course my integral is 1, or using the square root, I didn't simplify it. But the integral, where's the integral? Well, the integral was done, and it was 1. I must have left it off here. It's on this next one, though. So that'll be good enough. So with Pluto, there's the easy way to do it. Why recenter? Turns out recentering actually didn't make it easier. But if you don't recenter, so like there's your r's, I can still do the integral. Well, there's a plot of that, and now the integral, and its average value. So divide by the length of the interval will be 2. So the average value is 1. Which in general, it'll be a. So for Iris, there it is again. So the integral using with the focus at the origin is 1. Or the center at the origin, it's still going to be 1. It's linear. Didn't look linear, perhaps at first, but it was. And Halley's Comet. Average value is 1. Or with the center, the origin, the average value is 1. Oops, I didn't do that integral either, but it is 1. And then for the central angle, so there's my formula for the ellipse in polar form, centered at the origin. This is for Iris. And we want these r's. I'm going to skip that. Let's just get the integral. And then for the average value, I want to divide by 2 pi. Right? So if I integrate from 0 to 2 pi, divide by 2 pi, that'll give me the average value. It's 1, and in general, it's a. Or for Halley's Comet, see if I have anything good there. The integral will be that. It looks messy. I don't know how easily doable it is, but we argued without getting the integral that the average value is going to be a, and we can see that numerically as well. So to sum up, this is our result. So you can find the average value with respect to the sun, the angle with the sun at the origin, and the average value is going to be b with respect to that angle, or average value with respect to arc length. It'll always be a. Average value with respect to time. Average value with respect to projection onto the major axis, which I had as the x-axis, or the central angle, if the center is at the origin, that'll be back to being a. All right, so we beat that to death, but wanted to put it out there anyway. So I hope you enjoyed it. Hope you stayed till the end. And something to ponder for the rest of your day. Thank you.